Okay, hello everyone. Welcome to the problem solving session for week 11 on discrete maths course. So, what we'll do today is we'll look into some asymptotic and analysis, and we will also look into what are recurrence relations and how to formulate them, how to given a question. Okay, yeah. So we'll talk about what are recurrence relations. Given a problem, how do you formulate a recurrence relation and how to solve them? So one part is formulation and the other part is solving them. Okay. So we will define these terms as and when we come across it. So yeah. Okay. So we'll recall quickly what is the big O notation. So okay, so like you must have seen in the lectures, you're given two functions f1, f2, let's say, and you see the values in time. So let's say this is 5, then this becomes 10, then 15, 20, and so on. And the other function is behaves differently. Say it goes 5, 10, um, 20, 30, and so on. So this function is nothing but it's 5 times n, and this function is yeah, is 2 times um, f of n minus 1. Okay, so essentially this is 5 times 2 to the 0, this is 5 times 2 to the 1, this is 5 times 2 square, and so on. So this is 5 times 2 to the n minus 1. So notice that these two functions start off with the same values, but later on there is a point beyond which this function takes off very fast and this function is still not growing as fast as the other. So in general we're given two functions and we want to see which one is bigger. So you can't look at all possible values because those are typically infinite. So what you do is you appeal to what is called the big O notation. So what you do is if you plot them graphically, let's say f1 is a function that grows like this, and let's say f2 is a function that starts off with smaller values, but then there's a point beyond which the function takes off from that point. Let's call it n0, and after that point you are sure, after this point you're sure that whenever you look at f2 will always be f2's value will always be larger than that of f1. So in that case you say that f1 is order f2. So yeah, so that's all what that's how we compare two functions. So yeah, so essentially it's that there exists an n0 such that after that point f1 of x is at most c times f2 of x. Okay, so uh, yeah, so having defined that, you're given three functions. So f1 of n is an exponential function, it takes value 2 to the n. f2 of n is a polynomial function which is n to the 3 over 2, and f3 of n is defined as n log n. So you want to compare them asymptotically. So asymptotically in terms of order notation, which one is bigger than the other? So can you maybe take a couple of minutes and try this out? Okay, so you can write your answer in the chat, or if you feel like you can unmute and tell the answer. Okay, so let's try to solve this. Maybe I'll take a fresh page. So you have f1 of n is 2 to the n, f2 of n is n to the 3 over 2, and f3 of n is n log n. So okay, so let's try to write this differently. So this is already in the form of 2 to the n. So first we'll compare the functions f1 and f2. Now if we look at f2, this is n to the 3 over 2. So what I'll do is I'll write this as 2 to the log of n to the 3 over 2. And now what we'll do is we will compare. We know the base are same. The base is 2 for both of them. So we'll look at the exponent. So whichever is larger will be the so this is 2 to the 3 over 2 log n. So you're essentially comparing n versus 3 over 2 log n. So amongst these, which is larger? Is n larger or is log n larger? 3 over 2 log n larger? Okay, so notice that if you try to plot the values, it will be very apparent that if you just try with n equals 2, at this point n takes a value of 2, then this takes a value of 3 over 2. I think even in the first step this is larger. Now if say n is 3, then this is 3 and this is 3 over 2 log 3, which is still so I mean you can see from this point that log n is a very very slow growing function. So therefore n is n is definitely greater than log n, and therefore what you can say is f1n is asymptotically greater than f2 of n, or what you can say is f2 of n is order f1 of n. So so that tells you the comparison between f1 and f2. Now you want to compare between f2 and f3. So so f2 is n to the 3 over 2 and f3 is n log n. So this is same as n times n to the 1 over 2. This is n times log n. Now we're comparing between square root n and log n. Okay, now again we know that log n is a faster function than square root n is a much faster growing function than log n. So so this is also something that you can see by simple plotting or by taking limit. So since this is larger, you know that f2 of n is greater than f3 of n, or asymptotically f3 of n is order f2 of n. So by combining this, from here you know that f1 is larger than f2, and from here you know that f2 is larger than f3. So the answer to this question would be A. So in the order of us in the okay, maybe this is not the increasing order, this is the decreasing order. So the increasing order would be f3, f2, f1, because f2 is larger than f3 and f1 is larger than f2. So is this clear, or is there anything that yeah, are there any questions? Okay, so yeah, okay, good. So if there are no questions, we'll move on to the next one. So okay, so here's a question. What you're given is you have a 2 cross n square checkerboard. That means there are 2 rows and then there are n columns. So this is what it looks like. And you want to tile it. So what do I mean by tiling? I have a tile like this and I have another tile like this. So what do I mean by tiling? I can pick this tile and I can keep it here. So that way I would have covered this square and this square, or I can take this tile and I can keep it here like this. So then I'll be covering this and this. Or I could take this tile, for example, and keep it in the middle and cover this 4 squares. So this is what a tiling means. You are essentially, you have ample supply of tiles of both the kind, and you want to place them such that all the squares are covered. Now the problem is, if one tile is placed like this, you can't place another tile over here because you can't overlap 2 tiles. So given a square, only one tile um, can be placed over it. You can't have this rectangle and this rectangle like this, because that would violate the property. But you can have 2 rectangles like this, that is allowed. So that is the tiling problem. You have supplies of such tiles and you want to cover this area such that every square is covered and no square is covered by 2 tiles. So yeah, so you want to write a recurrence relation for this. So maybe yeah, so T of n, let's say T of n denotes the number of ways in which you can so how do we go about it? Any starting points? Okay, so what we can do is, if you want to tile this entire checkerboard, what you can do is, you can uh, tile this last column using this tile, and then your task reduces to tiling the rest of the 2 cross n minus 1 checkerboard. So this is a 2 cross n minus 1 checkerboard. And what you could do otherwise is that you can place you can place a square, this second tile here, you can take this second tile here and place it here, and then solve for the remaining tile. So that would be 2 cross n minus 2. So what is the total number of ways of doing this? The total number of ways of or maybe I'll call this T of n. The total number of ways of tiling is that either you place a rectangular 1 cross 2 tile, 2 cross 1 tile over here, and then solve for the rest of the problem. So that would be T of n minus 1. Or you can place a square tile here and then solve for the remaining 2 cross n minus 2 tile. So that would be T of n minus 2, and that is essentially the recurrence relation. And you're also asked to give initial conditions. So for example, what would be T of 1? What does T of 1 mean? You have a 2 by 1 checkerboard, and you want to find the total number of ways in which you can tile. So in how many ways can you tile this checkerboard? So there is only one way of doing that, because you have only one tile like this, and the only way to cover this is by placing that tile here. This you cannot pick because there is only a 2x1 checkerboard. So yeah, so there is only one way of tiling that, so therefore the answer is 1. Now let's look at what is T of 2. Okay, so this is a 2x2 checkerboard for and you want to find the total number of ways in which you can do the tiling. So so one thing you could do is you could already place your square tile here, that will cover all the 4 squares, and that is one way of doing that. The other way of doing that is you place your 2x1 tile here, that will cover the 2 squares, then you place your 2x1 tile here, that will cover your 2 squares. Or the third possibility that exists is you could take this 2x1 tile and place it horizontally like this and cover these 2 edges, and you could place another one like this and cover another 2 edges. So these are the only 3 possibilities in which you can cover a 2x2 checkerboard using the tiles that are given to you. So the answer for T of 2 is 3. And using these initial conditions and this recurrence relation, you can try to solve the relation and and find out a closed form expression. So what do we mean by closed form expression and how to solve the recurrences? That's something we'll look into it today, maybe after a couple of examples. But yeah, once we learn the technique, you can always come back and try to find a closed form expression for this. So you can find a closed form expression for T of n. Okay, so are there any questions about this, or this was clear? So please let me know if there are any questions. Okay, so we'll move on to the next question. And what you are given is, this is a slight generalization of what we saw. So now instead of okay, maybe let's take a simpler example. You have an n cross n checkerboard here, and you want to cover this checkerboard, and you only have L-shaped tiles. So what do the tiles look like? They look like this. So there are 3 tiles that are placed like this, and this is a single unit of tile that you have, and you want to stack them together and cover all of the squares such that no square is left and no square is covered twice. So in how many ways can you do that? Okay, so before if you try to solve this, you'll realize very soon that this may not even be possible. So sometimes it may not even be possible to tile it using L-shaped tile. So a simple example would be, you consider a 2x2 checkerboard, and now you keep your one L-shaped tile, let's say like this. Then there is one square that is left behind which cannot be covered now, because you don't have two other empty squares to begin with. So this cannot be tiled. So so what we'll do is, we'll generalize the question. So that's the motivation why we are defining a checkerboard like that. So what you're given now because this is not always possible, I'll give you a constraint where it's always possible. So let's say you have a checkerboard of size 2 to the n cross 2 to the n, and yeah, like that, and you want to cover, and additionally you know that somewhere in this checkerboard I have removed one square, so it could be here, it could be here, or somewhere. I mean, yeah, but all you know is there is a checkerboard of size 2 to the n cross 2 to the n, and one of the squares is removed. Now what we're asking is, in how many ways can you tile it using an L-shaped tile? So first of all, the existence itself is not clear. Why should you even be able to do that in general for any checkerboard of the given size? But yeah, but that's what a part of the question is. So one thing is to show the possibility. The other question is, in how many ways can you do that? So can you try to use recurrence in this case and come up with yeah and come up with a recurrence relation? Okay, so let's understand how to solve this. So let's think of this 2 to the n cross, let's divide this into two parts, like that. So what you have now, you have divided it like this and like this. So now you have four checkerboards like that. And what are the dimensions of these checkerboards? The dimensions are 2 to the n minus 1 cross 2 to the n minus 1, because there were 2 to the n rows earlier and you have divided into 2. So this will have 2 to the n minus 1 rows, this will have 2 to the n minus 1 rows, and similarly for the columns. Now so now I want to tile this thing. So what I'll do is, I'll try to convert this problem into the problem that is given to me. So what is the difference between this and that? So you're given a rectangular checkerboard with these dimensions, and you know that one of the squares is removed. So what I'll do is, I'll take my tile, L-shaped tile, and I'll place it here so that it covers this, covers this, covers this, and leaves this empty. Okay, and okay, before that, okay, maybe I missed one step. So the one step is that you know that one of the squares is removed from the checkerboard, and so without loss of okay, so maybe let me assume that this is the square from which there is a missing piece, there is a missing square. So what I'll do is, I'm looking at this four squares here, and I'll take my L-shaped tile and place it like this. So why am I doing that? So that if you look at this particular checkerboard, now the question is, you want to do a tiling of this checkerboard with one square removed, which is covered by this L-shaped tile anyway. So this translates to the question that the type of questions that we are given. Similarly, the same thing holds for this checkerboard. Because it's a 2 to the n minus 1 cross 2 to the n minus 1 square, and this square is removed because it's already covered with an L-shaped tile. So this also translates into the same problem but with a smaller size, and same thing goes for this. And what about this one? For this one, notice that this square is not covered by the L-shaped tile, but we already know that there is a missing square in the entire checkerboard which is lying in this quadrant. So this is already having 2 to the n minus 1 cross 2 to the n minus 1 dimension, where one square is already removed. So now you have four sub-problems which, if you can individually solve, you'll get a solution to the entire thing. So T of n would be that you place your square here, you place your rectangular tile here, then you solve your four sub problems for n by 2, and Yeah, and that's it, plus some order one time. So why is this n by 2? Because the original size that you have here is 2 to the n, and the size that you have here for the subproblem is 2 to the n minus 1, which is 2 to the n over 2. So I'm just replacing 2 to the n with a small n, and that's why this recurrence relation would come about. So yeah, so is this fine? I jumped 2 steps here, but is this fine? Is there is the idea of defining the subproblems and uh, the recurrence relation, is that clear? Okay, so good. So yeah, so that was the whole idea. What we did is, given this question, we divided it into smaller subproblems of similar kind, and to do that, we had to do some surgery here. We had to place an L-shaped tile here so that the problems are of the same kind. And then we individually solve for the problem and then take an order one time to combine them. So yeah, so that was about that question. And yeah, so we'll do some examples about counting. Okay, so okay, so let's say you have a huge chessboard. So a general normal chessboard that you have is generally 8 cross 8 dimension, but you can always think of it, you can think of a larger chessboard which is of the dimension 100 cross 100. So there are 100 rows and 100 columns, and then small squares like that. And you also have a large number of chess pieces. So now what you do is, you want to place rooks on the board. So you have k many rooks and you want to place them on the board, but you can't place it um, there are certain rules that you have to respect. So for example, I can't place my first rook here. Okay, I can place my first rook here, but then I'm not allowed to place my second rook here, here, and anywhere along this row, and along this column, and anywhere along this row. Why is that? Because I don't want the rooks to attack each other. So you know that if there is a rook here and there is a rook here, then one can take the other, or in other words, they can attack each other. So I don't want my rooks to attack each other. I want to peacefully place them such that then none of them attacks any of the other. So for example, if I keep my second rook here, there's no problem because none of them, they cannot attack each other diagonally. So that's a question. You have k many rooks and you want to place them such that they don't attack each other. So one way would be that just place them along the diagonals like that. So for just go up to k and place the k rooks along the diagonals, and that would be a non-attacking position. So the question is, in how many ways can you do that? So this is just one way of doing it, and we're interested in counting in how many ways can you do that. So yeah, so maybe just take a couple of minutes and try to solve this, and then we can discuss the solution. Okay, so let's try to understand. So notice that if you want to place k rooks, then you have to choose k rows in which you can place them, because no two rooks can be in the same row, otherwise they would be attacking. So you want to choose k rows out of 100. So in how many ways can you do that? You can do it in 100 choose k many ways. Similarly, the same argument symmetrically applies to the columns. You can't place two rooks in the same column, because otherwise they would end up attacking each other. So you have 100 columns and you want to choose k out of them. So you want to choose k columns out of 100, and this can be done in 100 choose k ways. And yeah, and now is it okay if I just say that, okay, you have chosen your k rows, you have chosen your k columns, so it will, let's say, look something like this. Maybe it's this this set of k cross k where you're going to place them. So is it fine if I say that the total number of ways of placing the non-attacking rooks is 100 choose k square, or is there something that we're missing? So the point is that we have chosen, so let's say we have eliminated some part of the checkerboard, and we now have a nice k cross k checkerboard where I'm going to place them. But this just tells me that these are the rows in which the rooks are going to appear, these are the columns in which the rooks are going to appear, but does not tell me for this choice of row which column should I place the rook in. So there are k many choices for me to place the first row, but let's say I placed it here. Now for the second row, I'm going to have to place a rook on the second row, but I don't know which column to do it in. Should it be here, 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 and so on? But we definitely know for sure that it cannot be on this particular cell, because otherwise these two would end up attacking. So there are k minus 1 free choices for the second rook to be placed. This is for the first rook, this is for the second rook. For the third rook, now let's say I placed it here. Now the third rook cannot be placed here, it cannot be placed here, so there are k minus 2 choices for it. So for the third one we have so this is k minus 1 and this is k minus 2, and so on. So finally for the kth rook, what will happen is k minus 1 positions will be blocked, and there will be only one cell that is left free, so that will be 1. So these are independently done. So for every choice of k choices here, you have independent k minus 2 choices here, and therefore the total number of ways you can do it is k minus 1, k minus 2. This is the rule of products that we apply, and this is same as k factorial. So essentially you are choosing the cells, the rows and columns in 100 choose k square ways, and then you are multiplying it with k factorial, so that to arrange for which row, which column should in each row which column should the rook go to. So this is the total number of ways in which you can do this. So I hope that is clear. So what we did is we first chose the rows, we chose the columns, we then came up with a permutation and multiplied all the answers to get this. Okay, so if that makes sense, we can move on to the next question. So what we saw so far is how to design recurrence relations given a problem. So it makes your life very easy. Rather than solving the problem with a brute force or something, you essentially are taking help of smaller and smaller sub-problems to solve the bigger problem. That's the essence of the recurrence relation, and it's used extensively in the area of computer science, and it does appear almost everywhere. So yeah, so now the question is, we've designed the recurrence relation, but I want to know what is the exact value at a point. So to get that, I'll have to solve the recurrence and find a closed form expression for the same. So yeah, so what I'll do is, I have this t of n is 2 times t of n over 2 plus order n. So this is an example, and what I'll do is, we will simply try and expand the expression. So what would t of n over 2 look like? T of n over 2 would be 2 times t of n over 4 plus order n, order n over 2, which is same as order n. So maybe I'll just write this as maybe I'll write this as Cn for a constant C, and I'll write this as Cn over 2. And now I'll take this expression and plug it here. So what does t of n become? T of n is 2 times t of n over 4 plus Cn over 2 plus Cn. And now I'll multiply this nicely, so this becomes 2 square times t of n over 2 square plus Cn plus Cn, and that is what your value of t of n is. Now what you do is you expand this further. So this is 2 square outside, and by definition what is t of n, and t of n over 4, it is 2 times t of n over 8 plus c n over 4 plus Cn plus Cn. And now this will turn out to be 2 cube t of n over 8 plus Cn plus Cn plus Cn. And now what you can see is there is a pattern here. So what's happening is every time you substitute this here, you get an extra factor of Cn out here. And yeah, so this is 2 t of n over 2 cube plus 3 times Cn. And what will happen is, if you keep on doing this, ultimately this problem is getting smaller and smaller and smaller. So first you are halving it, then you are halving it further and further and further until this becomes a constant size problem, which you can trivially solve. So when will this terminate? This will terminate, let's say, after k steps. Let's say n over 2 to the k becomes a trivial size problem. So what is the value of k? K should be log n. So after log n steps, this process is going to terminate, and what will t of n then look like? T of n will look like 2 to the k, t of n over 2 to the k plus k times Cn, and this is same as 2 to the log n times t of n over n plus k times Cn, and this is nothing but n plus kCn, which is again order n. So k was log n for us, right? So k is log n, so I'll just substitute it here, c times log n times n. So this is order n log n. So this is the so this is the solution. This is how you solve the recurrence relation. So what we did is you basically started expanding this and started collecting the terms here, and then you observe this this relation, and yeah, therefore this is what you get. And once you substitute k to be log n, you I mean, you just wait until the problem becomes so small that it's trivial, and then substitute for that k, and then you get this as n log n. So if that is fine, we'll move to another example, which will make which will just give you more grip over solving such okay. So I'll read out the question. So the question is that you are given this relation t of n is t of n minus 1 plus 1, where t of 1 is 1. And what you want to do is you want to find a closed form expression for this, or it's asymptotic complexity. So so what you do is you do the same thing that we did earlier. What you know is t of n minus 1 is t of n minus 2 plus 1. And now I'll plug this value and substitute it here. So t of n becomes t of n minus 2 plus 1 plus 1. And now you do this further. So this would further become t of n minus 2. This is same as t of n minus 2 plus 2 plus 2 plus 1. This is same as t of n minus 3 plus 3. So if you keep on doing this further, at the kth step you will have that t of n is same as t of n minus k plus k. And now we ask the same question, at what value of for what value of k does t become very trivial? So if you choose k to be n minus 1, then t of n becomes t of 1 plus n minus 1, and we know that t of 1 that is given to be 1 here, so I'll use that and place it here. So this is 1 plus n minus 1, which is n. So that gives you the answer, t of n is equal to n, which is order n. So this is order n. So the answer is B. Okay. So the idea here was again similar. What you did is you started expanding the recurrence, and then you use the base case to get to the expression here. So we will do one more example of that kind. So okay, so the recurrence that is given to us is t of n is equal to 2tn minus 1 plus 1, where t of 1 is 1. And now we'll do the same thing again. So you try to substitute this. This is 2 times t of n minus 2 plus 1 plus 1. So this is 2 square times t of n minus 2 plus 2 plus 1. And now you expand this one step further, so you get 2 square times 2t n minus 3 plus 1 plus 2 plus 1, and this becomes 2 cube t of n minus 3 plus 2 square plus 2 plus 1. Okay, so if you do this for k steps, what you get is t of n is 2 to the k times t of n minus k plus 2 to the k minus 1 plus 2 to the k minus 2 plus, and so on up to all the way up to 2 to the 0. And again we ask the same question, for what value of k does the problem become trivial? So let's choose, like earlier, choose k to be n minus 1. Then what you get is, this becomes 2 to the n minus 1 t of 1 plus 2 to the n minus 2 plus 2 to the n minus 3, and so on all the way up to 2 to the 0. And we know that t of 1 is nothing but 1. So this turns out to be 2 to the n minus 1 plus 2 to the n minus 2, and so on up to 2 to the 0. And this is nothing but 2 to the n minus 1. This is just a geometric progression whose answer turns out to be 2 to the n minus 1, and that is order n 2 to the n. So this is order 2 to the n. So that's the answer for this. So the first question that we saw gave us a complexity of n log n. The second one was a linear one where you got order n, and the third one that you saw is what gives you order 2 to the n. So this is not the only method of solving recurrence relation, but this is an easy way of doing that, which may in this case it so happens that it easily gives you the answer, but each time it may not happen because the equations, the relations could be a bit more complicated. So there you need different tools to solve the recurrence relations, some of which we'll look into it further in this tutorial, but some of them, there are others as well that are equally interesting, but we may not be able to cover it due to in interest of time. So next what we'll do is we'll try to see how to solve these relations. So let's start with a very simple example. So what you have here is, sorry, oh, so what you have here is a relation that is given as a recurrence relation that is given like this. You have an is equal to 2 times 2 2 times an minus 1 plus 4, and you know that a0 is 6, so you want to find the value of a2 and a4. So one thing that you could do is something that we did just now. You could just substitute it. So a1 is 2 times a0 plus 4, which is 2 times 6 plus 4, which is 16. Then a2 is 2 times a1 plus 4, which is 32 plus 4, which is 36. So that gives you the value of 36. So a2 now is 36. Now I want to find a4. So what I'll do is I'll first find a3, which happens to be 2 times a2 plus 4, which is 72 plus 4, which is 76. And a4 is 2 times a3 plus 4, which is 152 plus 4, which is 156. So the answer for a4 is 156. Now this is a perfectly fine way of solving the recurrence relation, where you did the obvious thing, which is use the relation, use the previous value, double it and add 4. That's what we did. So double this and add 4, double this and add 4, and that's how you kept on getting. But the problem here is, let's say I want to find a of 4200. Then I can't directly find it, because I'll have to start right from a1, then I'll double it and add 4 to get a2, I'll double it and add and so on. So if I keep on doing that until I find this one value, I would have to solve this 4200 times in order to get the solution. So this is not a very elegant way of doing it. So one way to get around it is that you just do what we were doing earlier. This is what you know. Now you substitute further. So this would be 2 times an minus 2 plus 4, and that would be 2 square an minus 2 plus 4 times 2 plus 1. Then this further becomes 2 cube times an minus 3 plus 4 2 square 2 to the 1 2 to the 0, and so on. So after k steps, this would be 2 to the k an minus k plus 4 times 2 to the k minus 1 plus k minus 2, and so on up to 2 to the 0. And again, like earlier, you're going to choose k to be n. So this becomes 2 to the n times a0 plus 4 times 2 to the k minus 1, 2 to the k minus 2, and so on 2 to the 0. And k is n for us. Okay, so this again, you use the fact that a0 is 6, and that gives you 2 to the n times 6 plus 4 times 2 to the n minus 1. So this would become 2 to the n times 10 minus 4, and yeah, so that's the solution, 10 times 2 to the n minus 4. So now you know a closed form expression like this. So if you know this, and if I ask you, for example, what is the value of a4200, the 4200 term, then all you have to do is substitute it here and find your answer in one step. It's just a matter of squaring this, and you'll have your answer in one step, rather than having to first find a1, then a2, use it to find a3, and all the way up to a4200. So that is one reason why we are interested in closed forms of expressions, because you want to find the value at a particular point in one step, rather than having to have so many dependencies and so on. So this example was just to motivate why we are interested in solving the recurrence relation. So having understood that, let's understand what are a few nice ways to solve the recurrence relation. We may not look at the proof of it, but we will look at some nice ways of solving it. So okay, so let's take this example. So you are given this recurrence relation, and the recurrence relation looks like this. And you know that a0 is 1 and a1 is 6. Okay, so now what we'll do is we'll use the theorem that we saw in the lecture, which says that if you're given this, then what you do is the first step is that you write a characteristic equation for this. So what is the characteristic equation? The equation is x square minus 6x plus 9. So essentially you bring this down to the left hand side, you can think of it that way. Equate this with 0 and find the solution for this. So this is nothing but x minus 3 whole square, and therefore the solutions, the roots of this equation are 3, 3. So these are the roots of the quadratic equation that you have in hand. And now we know that if these are the roots, then the nth term of the recurrence relation would look like 3 to the n alpha 1 times 3 to the n plus alpha 2 times n times 3 to the n. So this is the solution that we know. So in general, if x1 x2 are the roots of characteristic equation, then the nth term would look like alpha 1 times x1 to the n plus alpha 2 times x2 to the n. But in this case, if it so happens that x1 x2 are distinct, and therefore you can write like this, but if they are the same, then the nth term has a factor of n in the other expression. So in this case we have the same roots, therefore we are in the second case, and therefore you have this extra n term here. Now the question is, what is the value of this alpha 1 alpha 2? So in order to find that, we'll use the base case that is given to us. You know that a0 is 1, so a0 is nothing but alpha 1 plus alpha plus 0. So therefore this is 1, therefore alpha 1 is 1, and a1 is alpha 1 times 3 to the 1 plus alpha 2 times 1 times 3 to the 1, and alpha 1 is 1, so a1 is 3 plus 3 times alpha 2, and a1 is 6, so alpha 2 is again 1. So alpha 1 and alpha 2 are both 1, therefore this gives an is nothing but 3 to the n plus n times 3 to the n. So the answer to this is C. So I hope that was clear. So just to repeat what we did, we wrote, given this recurrence relation, we came up with the characteristic equation for this. We found out the roots for it. We observed that those are not distinct. There are repeated roots, and then we plugged them into the appropriate solution for an, which is an is alpha 1 times the first root to the n plus alpha 2 times n times the second root to the n, and then we use the base case to find the values of alpha 1 alpha 2 and simply substituted it here. So the proof of this is not something that we did within the scope of the lecture, but but the point of this example is to demonstrate how to use it to find a closed form expression, which is well motivated by the previous example. So if that is clear, we'll do one more example for the same. So you have the recurrence relation an is equal to minus 3 an minus 1 minus 3 an minus 2 minus an minus 3, and you have been given the initial conditions for a0, a1 and a2. Now you want to find a closed form expression for the same. So maybe pause for a couple of minutes and try to solve this, and we'll discuss in some time. Okay, so let's try to let's start with the step 1, which is to get the characteristic equation. So that is x cube plus 3x square plus 3x plus 1 is equal to 0. And now I want to find the roots of this cubic degree 3 equation, and this is same as 1 plus x whole cube is equal to 0. Therefore the roots of this are minus 1, minus 1, minus 1. Again we observe that these are repeated squares, so these are not distinct squares, so we will use the second kind of solution. So that gives you an is equal to alpha 1 times minus 1 to the n plus alpha 2 times n times minus 1 to the n plus alpha 3 times n square times minus 1 to the n. And now we'll use this initial condition. So we know that a0 is 1, so a0 is substituting n is equal to 0, that gives you alpha 1 plus 0 plus 0, so you have alpha 1 is equal to 1. Now a1 is minus 2, and that is alpha 1 times minus 1 to the 1 plus alpha 2 times 1 times minus 1 to the 1 plus alpha 3 times 1 times minus 1 to the 1, and that is nothing but minus alpha 1 minus alpha 2 minus alpha 3 is equal to minus 2. And we know that we know that alpha 1 is 1, so I'll substitute it here. So what you get is minus 3 is equal to minus alpha 2 minus alpha 3, and so that gives you alpha 2 plus alpha 3 is equal to 2 minus 1, which is 1. So this is what you have. And now we'll use the third initial condition. So a2 would be alpha 1 times minus 1 to the n or square plus alpha 2 times n times minus 1 square plus alpha 3 times n square times minus 1 cube, and a2 is minus 1. So minus 1 is equal to alpha 1 we know is 1, so this is 1 plus alpha 2 times, this should be 4, I did not substitute it here, square. So this is alpha 2 times 2 plus 4 times alpha 3, and that gives you 2 times alpha 2 plus 4 times alpha 3 is equal to minus 2, that is alpha 2 plus 2 alpha 3 is equal to minus 1. I'm just dividing this by 2. So this is one equation that you have, and the other equation is what we wrote earlier. You know that alpha 2 plus alpha 3 is equal to 1, and if you subtract this, what you get is alpha 3 is equal to minus 2, and if you substitute it here, you get alpha 2 is equal to 3. So substituting all this here, you get that an is equal to alpha 1 is 1 times minus 1 to the n plus 3 times n times minus 1 to the n plus minus 2 times n square times minus 1 to the n, and if you collect these terms, this gives you 1 plus 3n minus 2n square whole to the minus 1 to the n, and that's the closed form expression for the for the n that you got. So again, this was a bit there was some calculation that was involved, but the idea is the same as what we did earlier. You have a characteristic equation, and what we did is we tried to find the roots of the cubic equation. We saw that there are repetitions, and hence you got this form. You use this form that we saw in the lectures, which tells you the closed form for the nth term. Then to find the values of these constants alpha 1, alpha 2, alpha 3, we used the initial conditions, substituted them, solved them to find the values, and simply plugged and placed this here. So the answer for this question is C. Is B. Okay. So I think that is more. So what we did today is we looked into a bit of asymptotics. We saw how to formulate recurrence relations, how to use them to solve the problems, and finally we saw how to solve the recurrence relation itself. So in today's class, there were also, in the beginning there were some expressions here that we did not explicitly solve, but now that you know the methods to solve them, it is a good exercise to try and solve this. And this, for example, yeah, so given this, you can try to use the ideas that we saw. So we formulated the recurrence relations earlier. You can use these ideas and try to find them explicitly. So that would be an interesting exercise. And I think, yeah, that is all I had for today's class. So next we will meet on Friday, 6 p.m. to 8 p.m. That would be the that would be the week 12, and that would be the final. Okay, so that is yeah. Mm, and there would be one additional lecture that we will conduct on Monday. That would be the final lecture. So this will be more like a summary of, if you've it will be a summary of whatever we did. We'll try to do examples of all kinds, one example maybe for each concept. So it will be more like a revision of the course, and hopefully we'll get some time to see something interesting, some interesting examples of how discrete maths does not end here but has a lot of interesting applications outside. So this will be the final class, and I'll announce this in the next lecture also. The timing is same, 6 p.m. to 8 p.m. So yeah, that's all for today. So okay, thank you.